For the design of any hydraulic structures, we should know the average rainfall of a rain gauges on a particular catchment area. For example, on a catchment area having nearly 50 rain gauge stations, out of 50 rain gauge stations, any one of the rain gauge station is inoperated a part of the month or entire month or in a throughout year, but we should know the rainfall data of a particular station. Here, the missing rainfall data is estimated by using the mean annual rainfall of the existing rain gauge stations that are also known as index stations, right? For the determination of mean rainfall data, we should know the mean annual rainfall of index stations that are maybe 3, 4 or 10 whatever existing on a particular station, right? Here the mean annual rainfall is nothing but average annual rainfall of a particular station. And also one more term used in the irrigation engineering, that is normal annual rainfall, is the average value of the annual rainfall over a specific period of 30 years. This normal rainfall is also updated for every 10 years. This will give the accurate value as compared with the mean annual rainfall as well as average annual rainfall. The missing rainfall data of a particular station can be calculated by using the three methods. One is comparison method, another one is the normal ratio method, and last one is the isohydraulic method. Comparison method, this is a very simple method. If we are going to estimate the missing rainfall data on a particular rain gauge station, on a particular catchment area, that in this system we are going to take the mean annual rainfall of nearest station or adjacent station. Here P represents rainfall of a station X, and P represents here also rainfall of a station A. Px divided by Pa equal to Nx divided by Na. N represents the mean annual rainfall of station X, mean annual rainfall of station A. So this is the simple formula used for the determination of missing rainfall data by using comparison method. Whereas in case of second method, normal ratio method, this is the method we are going to estimate the missing rainfall data on a particular rain gauge. We should know the more than one adjacent rain gauge stations. Here X is the missing rain gauge station, and A, B, C are the adjacent rain gauge stations. Right? For the calculation of missing rainfall data of a particular station, so we should know the mean annual rainfall of station A, B and C. Right, here we are going to use two techniques. First technique is when the index station's mean annual rainfall is within the mean annual rainfall of missing rainfall station, then we are going to estimate the missing rainfall data by using this formula. That means average of these three values. That means Px is equal to 1 by 3, bracket begin. P represents precipitation at station A, precipitation at station B and precipitation at station C. That means average of these three gives the missing rainfall data at a particular station. In another case, when the mean annual rainfall at each of the index station, that means nearest stations, differs mean annual rainfall of X, that means missing rainfall station more than 10%, then we go to apply the normal ratio method. So normal ratio method formula is, this is the formula of the normal ratio method. Px is equal to Nx divided by 3. N represents mean annual rainfall. Bracket begin Pa by Na, that means precipitation at station A divided by mean annual rainfall at station A plus precipitation at station B divided by mean annual rainfall at station B plus precipitation at station C and mean annual rainfall at station C. In case where are three, here only we are having three adjacent rain gauges or index rain gauges, if that are known as M rain gauges existing on a particular catchment area. then we are going to, this formula can be written as Px is equal to missing rainfall data at station X equal to Nx divided by M. M is the index station's strength. Bracket begin, PA by NA means P represents the precipitation, N represents mean annual rainfall, PA by NA plus PB by NB plus PC by NC plus dash 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 PM divided by NM. PM represents precipitation of stations M, and the precipitation, and N represents mean annual rainfall of station M. So here another method is a iso-Heighton method. Iso-Heights, this is the another method. This is accurate as compared with the earlier two methods. Iso-Heights are the represents contours of equal rainfall depth. For example, on catchment area having 50 rain gauge stations, so we are going to take the data of 50 rain gauge. That data should be earlier data. Based on that data, we are going to prepare the iso-Heighton map. Iso-Heighton map by using the earlier data. Here, this is the map of iso-Heights are. For example, this 10 represents the rainfall depth is 10 centimeters depth, and next one 11 centimeters depth, 12 centimeters depth, and 13 centimeters depth, 14 centimeters depth. So these are the contours of equal rainfall depths. For example, we required the, for example, that missing rainfall data is at a station nearly surrounding zone, that is around 11 centimeters depth. Then we are going to take this is, for example, this is the missing rainfall data, so that we know the missing rainfall data of this station. This station is average of these two. So this is the method used for the estimation of this another method used for the estimation of average rainfall, missing rainfall data on a particular catchment. Right. Here one problem. So here they have given some data for the determination of missing rainfall data on a particular area. A rain gauge station X was inoperated for a part of a month during which a storm occurred. The storm rainfall records at the three surrounding stations ABC was 75 mm, 59 mm, 85 mm respectively. If average annual rainfall of the station A, B, C and X are 750, 650, 850 and 700 mm respectively, estimate the storm rainfall of station X. Here they have given three surrounding stations rainfall depth, that means index stations rainfall depth, and they required the missing rainfall data at station X. Apart from this rainfall depths of surrounding stations 3, also they have given mean annual rainfall of these 4 rain gauge stations. That means A, B, C are the index rain gauge stations and X is the missed rain gauge station. Based on this data, we are going to estimate the rainfall of a particular inoperated rain gauge station. We have here the difference of that mean annual rainfalls of NA, NB, NC and NX are more than 10%. Therefore, we are going to use the normal index ratio method. Based on the normal index ratio method, we know the formula, that is Px is equal to Nx by 3 bracket begin, Pa by Pn, that means P represents precipitation depth, N represents mean annual rainfall, Pa by Pn plus Pb by Nb and Pc by Nc. Finally, all data we have. Nx means that mean annual rainfall of station X, that is given, divided by 3, 75, 59, 85 is the rainfall depths. And 750, 650, 850 are the mean annual rainfall of index stations. Finally, we have 67.8 mm of rainfall depth. That is the value of missing rainfall station. Here, you observed here that is precipitation at station A 75 mm depth, B 59 mm depth, C 85 mm depth, and Px precipitation at station X is 67.8 mm. This is almost all nearer to these values. Now we are going to discuss about computation of average rainfall over a basin. This average rainfall on a particular catchment area is determined where the rain gauge stations existing on a particular catchment area is more than 1. For the determination of average rainfall, for the computation of average rainfall over a basin, these methods are used. Arithmetic mean method, Thiesens-Polygon method and Isohytal method. Arithmetic mean method, where the rainfall is uniformly distributed over the entire catchment area, then we are going to use this method. Here P1, P2, P3, dash dash, Pn are the rain gauges stations existing on a catchment area. Then how to determine the average rainfall over the catchment area? This is the formula for the determination of average rainfall over a basin. Here P average equal to P1 plus P2 plus P3 dash dash Pn divided by Pn. This is the formula for the determination of average rainfall. Thiesens-Polygon method. The arithmetic mean method is the approximate method, since rainfall varies in intensity and duration from place to place. That means, for example, this is one catchment area, Rajam, Srikakulam. This entire area is one basin or one catchment area. The rainfall at this Rajam is 1 mm per hour, whereas in case of Srikakulam, the intensity of rainfall is 10 mm per hour. From place to place, intensity of rainfall varies, and also duration. The rainfall over the in this area, that is in the Rajam, that is 1 hour for given 1 hour duration. But whereas in case of Srikakulam, 10 hours rainfall falling on a same duration, same place. So that's why the rainfall varies intensity and duration from place to place. So here Thiesens-Polygon method, what apart from that earlier method is that here we are going to consider the area under that rain gauge station. Right? For that, this method is also known as weighted mean method. Right here, this is the procedure for the construction of Thiesens-Polygon. Here now we are taken 4 rain gauge stations, rain gauge station A, B, C, D. Then these 4 rain gauge stations are joined, adjacent rain gauge stations are joined by straight line. This is one straight line, this is straight line, this is straight line, this is another straight line. Then these lines are bisected by lines. This is one bisector line, this is another line, this is one another line, this is another line. Then join the catchment area by like this. Then here what is happening, the area having, this is the under this rain gauge station, the entire area is under this rain gauge station. Then this entire area is under this rain gauge station B, and this entire area comes under rain gauge station D. This entire area comes under rain gauge station C. Then here what is the difference as compared with earlier method is, here we have determined area and prepared polygons, Thiesens polygons. Then how to determine the average rainfall? Right here, based on this area, we know the area here, point rain gauge station A, B, C and D. Then this average rainfall is A1 into P1. In earlier case, we have considered only P1, that is the rainfall depth on a particular area. In the Thiesens-Polygon method, rainfall depth on a particular catchment area, plus that apart from that area also consider what is the area under the rain gauge station. Here this is the A1 is the area under the rain gauge station 1, P1 is the precipitation at the rain gauge station 1, plus area under rain gauge station 2, precipitation rain gauge station 2, like that. This is the P3 dash 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 A and Pn divided by area of all rain gauge stations. Then we have the average rainfall over a catchment area. This is one example problem. Here this is the rain gauge station A, B, C, D. Right, this is the area under each rain gauge station. Rain gauge station A having catchment area is 45 square kilometers. B station 38 square kilometers, 30 square kilometers and 40 square kilometers. This is the area under each rain gauge station, and also rainfall depth on each rain gauge station A having 30.8 mm rainfall depth, 34.6, 32.6 and 24.6. These are the rainfall depths. So for the determination of average rainfall, what we are going to do, that area multiplied with rainfall depth. This is the area multiplied with rainfall depth. We have this one. These are the values of area into precipitation. Then finally the average rainfall equal to 30.5. The each range is 30, 34, 32, 34, 34.6. Here the average rainfall is 30.5. The last method, this is isohytal method. Already we discussed about Thiessens-Falcon method. This is also accurate method, but some conditions this is not giving accurate values. That means that rain gas station area is completely closed to the polygon. Then only gives accurate values. Where the rainfall is controlled by topography or results from the intensive conversion, then the values are not accurate by using the Thiessens-Falcon method. Then we go to isohytal method. Right? This isohytal method is the most elaborate and accurate in such conditions because the rainfall is controlled by mount topography. Right? What is isotrope? Already I told you, isotrope is the line or the contour connected equal rainfall depths of the all rain gauge stations. Then here also, as like as Thiessens-Falcon method, isohytal map shows the contour. Like that, this is the procedure for the construction of the isohytes here. So from the rainfall values recorded at various rain gauge stations, that is already existed available data. Based on that, first of all, we are going to prepare the isohytal map. Then measure the area enclosed between successive isohytes. That means this is one isohyte, this is another isohyte. The area between these two successive isohytes, measure the area by using planometer. Then this area multiplied with this area multiplied with the average of rainfall. That means here rainfall is 10 mm, here rainfall is 11 mm. The average of rainfall, these two isohytes divided into area, divided by 2 into area, we have the rainfall depth in a particular zone. Like that, for example, this is the 12 mm rainfall here, 13 mm rainfall here, 12 plus 13 divided by 2 into this area. That area in between the isohyte 12 and isohyte 13. Like that, you are going to estimate the area and the precipitation. Then you have the final, that means average rainfall is sigma A into P1 plus P2 by 2 divided by total area. This is about computation, estimation of average rainfall over the catchment area. Right.